The objective of this video is to look at a long-term example where we're finding the force per unit length. So we've been given this profile of soil where there's a retaining wall over here. The soil depth is 6 meters. We have a water table at the top and a water table at the left-hand side here. And we're going to say that this rock layer is very permeable. Okay? So what do we have? And we asked to find for the condition of minimum force. Minimum force was when we had sigma h min, and this was an active failure. So the minimum force is active. If they ask for the maximum force, it would be a passive failure. So we need to look at the conditions we have to determine if we're going to be doing an effective or total stress analysis. So we have long-term, we want to know the long-term, and we also have a clay. So long-term clay, it is going to drain, right? So we're looking at drain conditions, which means we need to do an effective stress analysis. Which means we're going to be using the parameters C dash and phi dash. So those values over there, we can ignore these values. If we were doing a short term, we would have to use these values, the undrained values, but we're doing long term. So what's going to happen now is obviously for an effective stress analysis, we need to know the pore water pressure, because we know that the vertical effective stress is the total stress minus the pore water pressure. But for a long-term example, what's going to happen is that the water is going to flow from this point to this point, because we're going to have different head values at those points, which means we're going to get flow. So it's not so simple to see the pore water pressure at different points. We're going to have to construct a flow net. So we're going to quickly draw a flow net. It's not too hard for this example. So let's say we put our datum at the bottom here. So here's our datum. Now we're going to get flow from this water table through the permeable rock to this water table here. So we can just represent that with vertical lines. So those red lines are our flow lines, and obviously for every flow net we also need EPs. So we need to make squares, so these are roughly squares, and these blue lines are my EPs. So what we can do now is we can find the head at the EPs, and then we can find the pore water pressure at the EPs. But before we do that, we need to find the maximum and minimum head values. So from our datum, if we were to stick in a standpipe, so if we were to stick in a pipe, how high would the water rise up above our datum for the top? So we get all this water rise, so it would rise to a point of 6 meters, which means that at the top of our surface, we have a head value equal to 6 meters. Now at the bottom, we have, if we were to stick in a pipe at the bottom here, that's where the water is flowing to, the water wouldn't rise at all because we're at the surface. Okay, so Z equals 0 and we've got nothing above us. So the head value at the bottom, the head value is equal to 0 meters. Okay, so now what we can do is we can find the head value at each of our EPs. So let's call this EP1, EP2, and EP3. So EP1 at 6 meters. So what we're going to have to do is find the change in head, the head drop. So we know the change in head will equal the big head, so the difference in head, which is 6 minus 0. So 6 minus 0 over the number of drops. So we have 1, 2, 3 drops. We drop once, twice, 3 times. So 6 over 3 is 2 meters. So our change in head from every EP to EP is 2 meters. So that means that the head here is 6 meters. We're going to drop by a change in head, which means that the head here is 4 meters. We're going to drop by another change in head, which means that the head at this one is 2 meters. And then eventually we'll drop by another head, which means that the head value here is 0 meters. So 6, 4, 2, and 0. So we've found the head at every single EP. Now we know that head is equal to pore water pressure on top of gamma of water plus Z. So we can find the pore water pressure by rearranging this equation. We've seen this before. So if we rearrange this, we would get H minus Z outside of gamma W. And now we can find the pore water pressure on our EPs. So if we were to do this, let's say we wanted to, so let's go EP2. So the pore water pressure along EP2. So at EP2, we have that H, we found H to be 4 meters, and Z similarly is 4 meters, okay? we'd scale this off and we'd come up 4 meters. And you can just see it graphically, right? We're going 2/3 of the way up of our wall, and 2/3 of 6 is 4 meters. So Z would equal 4, which means that our pore water pressure would equal 4 minus 4 outside of 9.81, which is 0. And you could do this for every single EP, and you will find that everywhere in here the pore water pressure is 0. So we have to confirm that. So therefore U equals 0 everywhere. So the pore water pressure is 0 everywhere. You can do this for EP3 as well. So if we just quickly did this, EP3, the head value of EP3, so EP3 is here, we found the head to be 2 meters. The Z value, so above our datum, is 1/3 of 6, which is 2 meters. So Z equals 2, which means that our pore water pressure similarly will be 2 minus 2 outside of 9.81, which is 0. So we have 0 pore water pressure throughout our system. So now we can go and find what we need to find. So we know that for an active failure, and if we're doing effective stress analysis, sigma H dash equals sigma V dash minus 2C dash square root N phi on top of N phi. So we can first find N phi, that's easy. N phi is 1 plus sine phi dash on 1 minus sine phi dash, which will equal 1 plus sine. Our phi dash is 20 degrees. So 1 plus sine 20 on top of 1 minus sine 20. And we'd get an answer of around 2.04. Now we will construct our table. So we'd have Z sigma V dash, which equals sigma V minus U, sigma H dash, and then eventually sigma H. So once again, we look at the top and bottom of our layer as always. So the top, okay, so now we're using the datum as our scale here. When we do this analysis though, when we come and do this table, we want to define a new axis. So we're going to come and make this Z, which means that the top of the layer is at Z equals 0, and the bottom of the layer is at Z equals 6. So we have 0 and 6. Now, let's do this first row. Sigma V is obviously just going to be 0. There's no vertical stress at all at the top layer. So this is just going to be 0. We know that the pore water pressure everywhere is 0, which means that our effective stress will be 0 minus 0, so just 0. And then we can find sigma H dash. Sigma H dash equals sigma V dash minus 2C dash root N phi on N phi. We found sigma V dash to be 0, so this is equal to 0 minus, and also C dash is 0. So this will be 2 outside of 0 root 2.04, which will obviously just be 0. And this is divided by 2.04. But because that's 0, our whole answer is 0. And that means if we were to find our horizontal stress, it would be the effective stress plus the pore water pressure, but the pore water pressure is 0. So it's going to be 0 plus 0, which will just be 0. We can then do the same thing for Z equals 6. So we will have a vertical stress now. So the vertical stress is gamma Z, which will be 20 by Z, which is 6 meters. So we would get 20 by 60. Sorry, 20 by 6 would get 120. So we would get a vertical stress of 120. We then know that U equals 0, which means that our effective stress will be 120 minus 0. So that will be 120. We could then find our horizontal stress. So sigma H dash equals sigma V dash, which is 120, minus 2, we know that C dash is 0, and we have N phi, which is 2.04, so on 2.04, so that's just using that equation there. We will work this out, so 120 divided 2.04, we would get 58.8. And then we could find our total stress by going 58.8 plus our pore water pressure, which is 0. So this would just be 58.8. So there we have our horizontal stress. We can now draw our stress distribution diagram. So it would look something like this. We have zero horizontal stress at 0 meters, but we have 58.8 kPa at 6 meters. And then we know to find our force, we just need to find the area of this, which is a triangle. So a half base times height. And if we were to work this out, 58.8 by 6 times a half, we will get 176.4 kilonewtons per meter. So in the long term, we're going to get a linear load of 176.4 kilonewtons per meter coming in and out of our page. So in this direction. Anyway guys, that's the long-term value. Just before I finish, if this were a clay example, we did a clay example. If we were to look at a sand example, because in the short term, for a sand, so if I write this down, for a sand, we saw in the previous set of videos that a sand in the short term was drained. Right? A clay in the short term was drained because it was quite permeable, which means in the long term it's obviously drained as well. So the values you would get for the short and long term are exactly the same. So this analysis of long term only really applies to a clay because you're going to get different values. But for a sand, the short and long term values of sigma h are the same. Anyway guys, hope that helps.